Hello everybody, welcome back to Whiteboard Wednesday, and today we will be doing this problem which says find the critical points and use the second derivative test to find any local minima or local maxima of this function right here. F of x equals 3/4 x to the fourth minus 5/3 times x to the third minus 6x squared plus 20x plus 7. So let's jump right on into it. The first step that we're going to want to take is to calculate the derivative of the function so that we can find our critical points. So we'll say f prime of x equals, just using standard derivative rules, 3x to the third minus 5x squared minus 12x plus 20. And again, we'll want to set this equal to 0 so we can find those critical points. And so f prime of x, here you will have to use some method of factoring. This one can be factored by grouping, and so I'll group these two together. So we'll have equals 3x to the third minus 12x minus 5x squared plus 20, and we can see that we can take out from this, we can take out a 3x, so we end up with x squared minus 4. And then likewise over here, we can take out a negative 5 minus 5. We get x squared. This is plus 20, but since we take out a negative 5, it changes to minus 4. And so then we can group these back here, so we have 3x minus 5, some reverse distribution right here. And so then we can see that f prime of x is equal to 0 when x equals, looks like 5/3, plug 5/3 back in there, yes, and then plus or minus 2. Okay, so we found our critical points. And then the question asks us to use the second derivative test to find any local minima or local maxima of the function. So of course we'll need to calculate our second derivative. So we'll say f double prime of x equals, so just take the first derivative of the first derivative here. So we get, let's see, 9x squared minus 10x minus 12. And so the second derivative test, which you've learned about in class, what you'll need to do is to plug in these critical points here into your second derivative, just in for x. And you'll want to take note of the sign that you get for what f double prime of these critical points is. So we'll take a look at that here. F double prime of 5/3 equals 9 5/3 squared minus 10 5/3 minus 12. And so simplifying this, we get 9 times 25 over 9 minus 50 over 3 minus 12. So we can cancel out the 9's here, so we get equals, and then we can do 25 minus 12 to get 13 minus 50 over 3. And we can see that if we multiply this here, we get equals 39. We get the common denominator minus 50 over 3, which is going to be equals negative 11 over 3. So take note that if we plug in the critical point 5/3 into our second derivative, we get a negative result. So let's do that with the other 2 points here. So we have f double prime of 2 equals 9 times 2 squared minus 10 times 2 minus 12. This one's a little bit easier because we don't have any fractions. So we will just take equals 9 times 4 minus 20 minus 12. This is 36 36 minus 20 minus 12 is going to get you 4. So that's positive. Again, take note on that. And then f double prime of negative 2 is, let's see here, 9 times negative 2 squared minus 10 times negative 2 minus 12. And so on here, we get 9 times 4 minus, actually it's going to be a plus 20 because we have a negative and a negative, so we get a plus 20 and then minus 12. So we get 36 plus 20 is 56 minus 12 is going to get us 44 here. So again, that's greater than 0. And so if we go back to what we've learned about the second derivative test, it says that if we end up with a value for plugging in the critical point into our function, and if that value is negative, then that says that the graph is concave down, and so that would correspond to a maximum, a local maxima, or local maximum. So we'll say local maximum. Likewise, if we have a positive value, we plug a critical point into our second derivative equation, and we get a positive value, that's going to correspond to a local minima because our graph is going to be concave up. So here we have local minima and local minima. And so there we have it. We have found the critical points right here, and then we have found local maximum, and then a couple local minima right here. I guess we'd say local minimum since we're just talking about one. And then if you wanted to find out whether these were absolute minima or maxima, you would just have to do a little bit more research into the function that you're using, maybe graph it, see what its end behavior is. But yeah, we've solved the problem.